Hello, I am Dr. Paris von Lockett, and today I'll be talking to you about 2D and 2.5D modeling and element types in SOLIDWORKS. These are ways that we can actually take a 3D model and reduce the computational complexity of it based on characteristics of its geometry. Very useful tools, very useful applications in finite element modeling in general, so hopefully you'll get some good ideas to take away today. So this lecture focuses on 2 and 2.5D modeling techniques and the element types. We'll focus on plane stress and plane strain for calculation types that you might be familiar with, and also we'll talk about axisymmetric bodies. After this lecture, it's important that you can distinguish between plane stress and plane strain conditions. Hopefully you've done that before, and also discuss plane strain, plane stress, axisymmetric, and shell type elements, shell being sort of the most recently developed. As with everything technologically related, there have been tremendous advances in the development of finite element analysis over the past 50 or 60 years, and specifically in the implementation of use of 2D and 3D surface and 3D solid elements in FEA. Initially, these things were very rudimentarily designed mathematically. They could solve simple problems, but now we've been able to apply the mathematics to solve even more complicated problems that are fully 3D with elements that have a reduced geometry and therefore a reduced simulation time because they have less overhead, less degrees of freedom. Many problems that once required sophisticated analytical procedures and the use of empirical equations can now be analyzed through the use of FEA, and we'll examine a stress concentration problem for that today. One historical note of interest: in 1994, in April, Boeing introduced the most modern commercial jet aircraft at the time, the twin-engine 777. But the key here, the claim to fame, is that this was the first airliner to be designed entirely using computer-aided design techniques. So a big milestone for the industry, and since then things have only taken off even further. Now, even with these advances, people have to be very cautious, and users of FEA have to be very cautious because there's this tendency to accept the answer from the computer because it came from the computer. And also, as you've noticed, sometimes you actually generate these nice pretty pictures which are very compelling in their graphical representation of the results. So there's some caveats we have to think about and some sort of reservations we have to hold in mind. The first being that unlike line elements, where the analytical solutions and FEA solutions generally match because of the way the problems are formulated, much care must be taken with 2D and 3D surface and 3D solid elements because few analytic solutions can be easily obtained. Well, what does this mean? Well, if we go back to that system of equations that was required for 3D elements, that required material specifications, that required kinematics of where stresses and displacements are related, and also required us to be able to write our equilibrium equations in 3 dimensions with differential equations, it is very difficult to get a solution that's an analytical solution, closed form equation to compare to for an arbitrary geometry. Generally, these are on very simplified geometries, being rectangles, cylinders, spheres, rings, or disks. And most things that we use in engineering will vary from those typical geometries or those archetypical geometries somewhat. On the other hand, steps required to perform FEA using these 2D and 3D surface and 3D solid elements are in general less complicated than that of line elements, because as we draw the bulk geometry, all we do is ask the software to fill in all of the other elements, and the software does this for us. We do not actually have to assign directions or planes to the elements, assign what directions those planes are with respect to our global geometry, or assign those directions of the planes with respect to the part as we draw it. We can, but we don't have to. So in that sense, they're less complicated. So what are we going to do? Well, from here on out, this section this week, we'll examine the use of these 2D solid elements to solve some traditional problems. We'll also show you can reduce 3D problems into 2 dimensions if they satisfy some assumptions associated with that 2-dimensional surface or needed for 2-dimensional surface elements. So the key here is what can we reduce and what's required, or what assumptions have to be made when we do those reductions. All right, if we look at basic element types, we have four types of 2D elements. The first two we'll discuss are plane stress and plane strain. And as we said, these things are meant to reduce a 3D stress state down to a 2D stress state for analysis. So if we look over here at our 3D stress state, we have stresses in the normal, sigma x, sigma y, and sigma z. And then on each face, we'll have two shears, xy and xz here, yz and xz here, and then two more on the top. However, if we reduce this to, say, a state of plane stress, then on the right, our stresses only exist in one of these planes, here shown in the xy plane. So we have an x normal stress, a y normal stress, and then our mixed xy shear for our state of plane stress. If we're going to define this, then we would say that plane stress is defined to be the state of stress that the normal stress and the shear stress directed perpendicular to the plane are assumed to be zero. So in this case, anything coming out of or into the board of this surface would be zero. So to contrast this with our plane stress body, we can look at our figures here on the top of this right-hand side. In our plane strain body, you might have heard this sort of thick assumption where in the z direction, the dimension of the part is thick enough such that any changes of that z direction dimension would be divided by that dimension, which is large, and so the strains would tend to zero because they're normalized by a large value. So if we have loading in the x and y plane, this loading in the x and y plane causes deformation in the x and y plane. Normalizing that by our z dimension would actually drive that to zero. So it's a thick body, no strains coming out of plane, shear or otherwise. On the contrast, plane stress, which we talked about before, could have similar loading in the x and y directions. However, that loading in the x and y directions causes nothing appreciable stress-wise in the z direction because there's nothing loaded out of that plane. And so we would call this a thin body because we don't have stresses developed in the z direction. On the bottom here, we see then again plane stress and plane strain are equivalent strains, or I should say our resulting strains that exist, sigma x and sigma y, our normals, our tau xy, and our shear. We also have for plane strain, and we replace our stresses with strains. So we have normal strains, epsilon x and epsilon y, and then our gamma xy shear strain. Nothing out of plane in terms of strain here, and nothing out of plane in terms of stress here. And we can check the bottom for our definitions of our stresses, our definitions of what our strains. And if we have an XY state of plane stress or plane strain, we can see that all of our Z terms go to zero. So moving on to our third type, axisymmetric elements. Axisymmetric elements can be used to model axisymmetric structures, and these things are generally things like storage tanks, nozzles, nuclear containment vessels, pressure vessels, anything subject to a uniform internal pressure can be analyzed using it's a two-dimensional system that can be analyzed using axisymmetric elements. We can also analyze spinning disks or spinning objects that are spheres, spinning objects that are subjected to a centrifugal loading, where the loading is completely radial. The caveat here is that nothing can change in the theta dimension. So if we look at this representation here, we can see our strains, we can see our stresses. We have strains and stresses in our normal directions, r, theta, and z. We have a shear. The shear, however, is only in r and z because we cannot have distortion in the theta direction, although we can have a uniform normal stress in that theta direction, constant normal stress. On the bottom right, we're also showing another representation of how you might view axisymmetric elements. Here we've got a ring-type structure where one of the elements is actually shown here with 4 nodes, and just a planar section cut out of that ring. And you might see this number here, CAX4. Different programs use different nomenclature for their element types, and you sometimes can define what type of element you want to use in your model, and in doing so, you can restrict the numbers of degrees of freedom or the types of things that that element is able to solve for, but that can also allow you to reduce the complexity numerically of your model. And here we see things for plane strain, plane stress, and their nomenclature as well. So if you use something like Abacus or Nastran, you may be familiar with these, or if you eventually do use those things, you'll become familiar with those nomenclatures. For our fourth type, our shell elements. These are surface elements that usually have a thickness that is generally small compared to their other dimension. Mathematically, they're more accurate when that's the case. It's a very versatile type of element, and unlike plane stress elements, shell elements can have loads that are not parallel to the object's surfaces. So what does that mean? That means in something like this, where we've got our shell element, where we have nodes along the faces of the element, we can define moments, we can define forces in plane, and we can also define forces perpendicular to that element. So it's very versatile for a large number of applications, with the caveat, a fairly stringent one, that they have to be thin with respect to the other dimensions. So as I said before, maybe a little bit in passing, but it's important enough to sort of hone in on. Plane stress and plane strain analyses fall into two categories. These categories are usually divided along the lines of plane stress associated with members that are thin, plane strain associated with members that are thick. Both cases, the loads act only in the plane, and we do not look for any out-of-plane loading. However, in plane strain, we can have, in plane stress, we can have out-of-plane stresses, whereas in plane strain, we assume that the strains out of the plane, because it's thick, and normalized by that thickness dimension, tend to 0. Alrighty, what are we going to do with this? Well, we're going to use these types of analyses, or these 2D analysis, to examine a traditional classical problem. This is a plate with a hole in it. This is a problem that's been studied for a very long time. Circular holes, elliptical holes, holes that are ellipses that are flattened down to form cracks. All of these solutions are available analytically. All of these solutions have been cataloged for infinite plates and for plates with finite dimensions. And what we'll look at is a solution for a plate with a finite dimension. We'll look up the analytical solution to it. We'll calculate it in SolidWorks, and we'll compare the two to see how accurately SolidWorks can represent the solution compared to the analytical. It's a standard thing that's been done since the evolution of finite element methods. Usually they come out with what are called verification manuals, where they will solve problems where the solution is already known, it's been calculated beforehand, to show that their solution procedures, their algorithms that are all running in the background, can generate answers that we know to be true, and then you can apply their software to problems that you don't know the answer to and have a little more belief in the solution that you get from it. Okay, well, hopefully you've learned a little bit more about 2D and 2.5D elements, plane stress, plane strain, axisymmetric, and shell elements. We'll see in the next lectures how we can apply those things and use them in SolidWorks, generate some results, and then that'll give us another tool in our tool belt to become the best finite element modelers that we can be. Thanks again for participating. Hope you've learned something, and see you in the next lecture. Take care.